I'll try to work through these problems as quick as I can, just because I'm a little short on time. But I pulled your problems up, looked at them real quick. I'm going to start with problem number 3. If it'll load. Alright, find the indicated IQ score. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. Alright, it looks like we want to find the score, this X value where it would separate the bottom 90% from the top 10%, basically is what it is. It tells us that the mean is 100, standard deviation is 15. What you're going to need to do is we want to use the formula Z equals X minus mu over sigma. Then to solve for X, we want to solve for X in this formula. That way we'll have a formula for X. You would multiply both sides by sigma, and you have sigma times Z equals X minus mu. And now add mu to both sides, and you'll get X equals mu plus sigma times Z, or Z times sigma. And so the problem gave us a mean of 100, and it gave us a standard deviation of 15. So that's 15. Alright. We want to figure out the X value, so we have to plug the Z in. That would correspond to a probability of 0.9, right? This right here, this 0.9, so you got to go to your Z chart and see which Z value is closest to 0.90. If you look in here, the closest we can get to 0.90 is 0.8997. That's actually closer than 0.915. So let's look what Z that corresponds to. 1.28 is the Z that corresponds to. 1.28. So that's what we want to plug in right there. 1.28. Alright. And so that's going to be 15 times 1.28 plus 100, 119.2. Okay. And let's see, now let's go back to your problem. Say 119.2. This next problem, number 4, is exactly, well, it's very similar. The only thing is, this has the 0.65 on the right side. The way that our table works, we have to use areas cumulative from left to right. So the way that you work this one is exactly the same, except the Z-score, you don't look up 0.65. The area under this entire curve is 1, so the area right here that's not shown would be 1 minus 0.65. So that is 0.35. So that's what you want to look up in the chart, 0.35. Because the area in our chart is cumulative from left to right. So we want to get as close to 0.35 as possible. So 0.35, that's 0.352, 0.3483. That's 17 10,000ths off, and that's 20 10,000ths off. So that's closer. So negative 0.39. Negative 0.39 is what we would use in our formula. So same formula. I think we actually had, do we have the same? Yeah, we have the same mean and standard deviation. So we get X equals 100 plus standard deviation 15 times negative 0.39. Alright, so 15 times 0.39 negative equals, and now add that to 100. Alright, 94.15. That's what we're looking for on that one. Alright, then I believe you said 7. Yeah, okay, problem number 7. Assume adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 20. So standard deviation is different here. Find P3, which is the IQ score separating the bottom 3% from the top 95%. So if you think about that under our normal curve, the bottom 3% will be down here. So an area of 0.03% is on the left side. On the right side, we'd have 97%. Well, what are we actually looking for? We want this x value that would have 0.03 to the left of it. So if you look up the z-score that corresponds to 0.03, z equals, let's figure that out first, 0.03. So look in here, look, 0.03. There's 0.0301. That's negative negative 1.88. That's a z of negative 1.88. We're going to use the same formula because we're looking for an x value. So that's x equals, we had a mean of 100 plus we had a standard deviation of 20 times a z-score of negative 1.88. Alright, so 20 times 1.88, make that negative, plus 100, 62.4. Alright, so that's your answer on that one. The next problem, number 8, you got that one right. Number 9, alright. So men's heights are normally distributed with a mean of 70.2 inches and a standard deviation of 2.8 inches. Women's heights are normally distributed with a mean of 63.9 inches and a standard deviation of 2.5 inches. The standard doorway height is 80 inches. What percentage of men are too tall to fit through a standard doorway without bending, and what percentage of women are too tall to fit through a standard doorway without bending? Alright. So, let me open up a new page real quick. For the men, we have a mean of 70.2 and a standard deviation of 2.8. The x in our formula is 80 inches. Okay, and so let's see what z-score that would correspond to. Remember, it's x minus mu over sigma. So that's 80 minus 70.2 over 2.8. Alright, and my calculator, 80 minus 70.2 divided by 2.8. Alright, so they would have to be above 3.5 standard deviations. Right, so z equals 3.5. So if we look at our table for a z-score of 3.5 and we want to know greater than 3.5, alright, and so If you look up 3.5 in the table, you actually get a value of 0.9999. We're looking for greater than that. So under the curve here, under the bell curve, we'd have about this much right here. That would be 0.9999. And if we want to know greater than that is this stuff over here. So you say 1 minus 0.9999. That's 0.0001. As a percentage, that'd be 0.01%. So 0.01% of all men would have to bend coming in an 80-inch door, which kind of makes sense if you think about it. A door that's 80 inches tall, there's not going to be very many men that's going to have to bend to come through that door. Alright, women, it's probably even going to be less than that, because, here, let's see. Women's height will be distributed with a mean of 63.9. I mean, it's going to be virtually zero for women, because, think about it. If the mean, let's see. Sorry about that. For women, we have a mean of 63.9, standard deviation of 2.5. So 63.9, standard deviation of 2.5. So you can see the z-scores are going to be even bigger because we have the same x, it's the same doorway. So 80 minus 63.9 divided by 2.5. So that's an astronomical z-score, 6.44. We use the same value in the table. If you were using technology, it'd probably actually show you like 0.00000001 or something like that. But as you can see on our table, the table says 3.5 and up. So you would technically, if you're using the table, you'd have to say 1 minus 0.9999 again to be 0.0001. Okay. And so, if a statistician designs a house so that all of the doorways have heights that are sufficient for all men except the 5%, the tallest 5%, what doorway height will be used? Okay, so the tallest 5%, and we're talking about men, so we had this statistics for men was 70.2 and 2.8. Mean equals 70.2 and standard deviation equals 2.8, and it said it wants all but the tallest 5%. So what we need to do, we're looking for an x value for the door. The tallest 5%, if you think about a bell curve, we want 5% to be on this side here. 5% is 0.05. Remember, our tables are cumulative from left to right, so if I want this x value that's in from the table, I have 95% to the left. So I actually look up the area of 0.95 in my table and get that z-score. I know I wrote an x there, but there's some z there. And so if I use my table, go back here, go to my table, I want to go to 0.95, as close as I can get to 0.95. You see there's actually a star there, and if you follow that down, I can pull this up some. My window is not allowing me to adjust it, but if you look at your chart, and you follow that down. I don't know if you can see it, it's getting cut off here. It's 1.645. 1.645 is that Z. So look at your chart, you should be able to see that. I just can't pull it up any further. So that Z right there is 1.645. And want to figure out what X value, how high would that door have to be? Remember, we solved earlier for X in that same formula. X equals, what was it? It was mu plus Z times sigma. So the mean is 70.2. The Z is 1.645. And the sigma is 2.8. Alright, so that's 70.2 plus, I usually do the second part first, but I'll just put it in parentheses. Parentheses 1.645 times 2.8. And I think I messed that up. Let's see. I think I typed that in wrong. Sorry about that. I'm going to redo it. Alright. Like I said, I usually type in the second part first. It may have been right. I don't know really. Let me retype it in though, just to be safe. Sorry about that. Just trying to rearrange these windows here. So you can see what I'm doing. I usually do the second part first. 1.645 times 2.8 plus 70.2. Alright, so 74.8 inches. That's how high that the door could be, so that all but 5% of the tallest men could get through the door. I hope that helps. If you have any other questions, please send them to me and I'll get them done as soon as I can. Thanks.